Okay, unilateral profile tolerance. Okay, so it would be specifies when an unequally disposed profile symbol, the unequally disposed value, either 0 or equal to the profile tolerance zone, indicating the amount of zone that adds material to the true profile. The entire tolerance zone is specified to either increase or decrease the material, and it lies entirely on one side of the true profile. The manufacturing target typically cannot coincide with one tolerance boundary. Okay, the dynamic profile tolerance indicates a specified profile tolerance form, but not the size. The symbol is the Greek letter delta, looks like a triangle. Okay, and the true profile is permitted to expand or contract in a uniform manner. And the profile tolerance zone remains related to the true profile and used in combination with another profile tolerance that controls the size. Okay, non-uniform profile tolerance zones. It varies proportionally over the full extent of the application or between modeled or labeled extents. Specified using supplemental geometry in the model, and non-uniform in place of the tolerance value in the profile feature control frame, and specified by labeling the extents in the orthographic view. Achievable levels of profile tolerance single segment. Profile tolerances can establish a variety of controls on part features. Feature control frame, primary factor in determining the level of control, and datum feature references may be customized. A significant amount of flexibility to express required level of tolerance control, and take care not to overspecify. Okay, form and size. Surface profile is typically used, and profile tolerance must not contain datum feature references. And the profile tolerance zone is not constrained, and other tolerances must establish location and orientation. Form, orientation, and location. Profile controls the form, not the location or the orientation. The datum feature references constrain the translation and rotation. The true profile is defined by basic dimensions, and the profile zone defaults to equal bilateral and is centered on the true profile by default. Okay, profile applied to conical surfaces. Only tolerance type to control conical features. The only form controlled if no datum feature references. And additional geometric controls to establish location and orientation. The size, form, and orientation and location are controlled if one or more datum features are referenced. Okay, profile applied to coplanar surfaces. Raised bosses can be used to create coplanar mounting surfaces. Coplanarity requirements for multiple features through profile tolerance specification. And well-defined meaning regarding form, coplanarity, and constraints of translation and rotation where applicable. So coplanarity, orientation and location, single segment surface profile tolerance when coplanarity, orientation, and location of a group of features is equally important. So here they're showing a bunch of different features, and they're controlling the profile in reference to a flat plane, which is datum A, and the features on the top of the part need to be within 8,000ths form of each other. Okay, the profile relative to datum plane established by control features. The datum feature with an equal bilateral profile tolerance that references that datum feature can only use half the specified tolerance zone. And consider applying a general note that specifies a profile tolerance that applies to the reference datum features. So we're controlling datum plane A and B, but the way it's called out, it's also controlling. It's controlling the three places of it. A profile relative to a datum plane established by datum targets and controlled features. So the tolerance is applied to multiple features where one or more datum features references are made to datum targets. And the tolerance zone is centered on the true profile, and the entire tolerance zone is available at all locations except for the target points themselves. So they're exempt. So achievable levels of profile tolerance with multiple segments. So what we have here is a multiple segment composite frame here, and it's referencing 18,000ths surface profile tolerance to datums A, B, and C, but it's holding a tighter tolerance of 7,000ths in reference to datums A and B. Okay, the multiple segment feature control frame is similar to the ones for composite position, and only one tolerance symbol will occur. And the multiple symbols indicate multiple single segments that establish different requirements. So that's the difference between the composite frame and a multiple segmented one. We've only got one profile symbol, so we interpret that differently than if we had two different frames with two different profiles. This applies to the entire feature in two different contexts, whereas if it was two separate frames on the left with a profile on each, they would just be specifying different areas of the model surface or part. Okay, composite profile tolerances. The datum feature references in the first segment constrain the translational and rotational degrees of freedom. So when you have multiple segments, the first one is going to control its rotation and how it can move around. So it's generally a looser tolerance. The second segment references constrain only the rotational degrees of freedom. And the upper segment is a profile locating for a single feature, profile pattern locating for pattern features. And the lower segment profile features for single features, profile features, and patterns of the feature. So the upper segment is going to locate the shape, and the lower segment is going to control the actual features of their size. Okay, it's very similar to how position works. Okay, second segment, no datum feature referenced. So the first segment to specify relatively large profile pattern locations, and the second segment establishes the profile feature relating tolerance without constraining the rotational degrees of freedom. So we have a looser tolerance again on the outside and on the first segment and the second segment, because it doesn't reference a datum. It just controls the profile itself without any rotational orientation. Okay, second segment datum feature is referenced. The form of coplanarity orientation with the same relative small tolerance. first segment allows greater tolerance for location of the feature, and the lower segment, specified with one or more datum feature references to constrain the needed rotational degrees of freedom, and the profile feature relating tolerance zone, control form, coplanarity, and orientation of the tolerance feature. Okay, all around feature with one datum reference. So composite profile applies to enclosed features with tolerances applied all around one datum feature reference in the lower segment. Okay, so here's an example of a composite profile, and it's the first line is saying, okay, your profile zone of the entire profile has to follow within this 80 thousandths zone, and it locates in this case the window or hole in the part. Then the second frame controls how much variation can actually be on that profile on the features itself. You notice it's a tighter tolerance. Okay, the all-around two datum feature references. The composite profile is applied to the enclosed feature with a tolerance applied all around and two datum features referenced in the lower segment. So it's the profile feature tolerance zone is constrained only in rotation relative to datums A and B. All around feature dynamic profile with two datum feature references. So the composite profile applied to an enclosed feature with tolerance applied all around, and dynamic profile specification in the lower segment with two datum feature references. So this allows the theoretically perfect profile to move more in orientation and size, but then the profile tolerance itself is tight. Okay, composite profile example applied to a pattern of features that profile pattern locating. So in this example, we have a pattern, profile pattern tolerance zones that are true profile locations relative to one another and constrained in translation and rotation to the reference datum features. So the first frame says, okay, we have two windows here, it's a pattern, both have to fall within this larger tolerance of each other. Okay, and then composite profile applied pattern features to feature related, the lower one, the profile zones of the true profile locations relative to one another are constrained only in rotational to the reference datum features, but not to each other. So you could have one vary on one end of the tolerance and the other one vary to the opposite side. Okay, multiple single segment profile tolerances applied to individual features or patterns of features, and each segment has profile tolerance symbol, and each segment is interpreted as a single segment feature control frame, and there's no consideration of other segments. Tolerance feature must meet the requirements of all the segments, and individually notation means that a segment applies to each feature independently of each other. So it breaks that pattern relationship between the different features. Okay, so profile and position tolerances combined. If you want to make it even more complicated here, you can do both. The profile tolerance applied establishes the size and form of the piece, the feature. The reference datum features must not be able to constrain translation to avoid conflict with the position tolerance. And the position tolerance is applied to control the location of the profile at maximum material boundary. And it permits the profile tolerance to be larger or smaller than the position tolerance. So if you don't care so much about the size of the feature, in this case it's a window going through the part, but you want to hold the position very tight, this would be the method to use. And the position tolerance creates a virtual condition boundary. Okay, the basic surface location, dimensions, and profile tolerances. They establish clear communication requirements with only one correct interpretation. They have to be related to the datum reference frame. It avoids ambiguity caused by directly applied plus and minus tolerances, and eliminates differences in accumulation caused by baseline or chain dimensions. Profile tolerances and additive manufacturing. So new design concepts and lower production costs are possible. They reduce the number of necessary parts and must know the importance of internal feature characteristics to correctly determine the applied tolerances. The new standards most likely developed in the near future. So that's where we're going with this. You make your thing with that additive manufacturing. It doesn't have a whole lot of flat features on it to measure. They model it, you hold it to surface to profile tolerance, and then you check it on a coordinate measurement machine. Okay, past practices. These are things you might see but are not part of the current standard. Profile tolerances were used in conjunction with coordinate tolerances to control form and orientation relative to datums. It's not used in the current version of the standard. Interpretation subject to debate and only needed for awareness of use on drawings created in the past. So you'll need to know that standard if it says a date on it older than 2018 on the standards. And avoid continuing that practice when revising an old drawing. So the idea is that you uprev it to the current standards. So yes, this past practice of having a tolerance to a corner where the surface starts is something that we don't do anymore. Okay, in summary, profile tolerances allow for precise control of features, form, orientation, and location by defining allowable variation within a specified zone. In this lesson, you learn to define both line and surface profile tolerances and apply them to control a variation either locally or across an entire feature. We covered how to apply profile tolerances that extend all around a part or all over its surfaces, and how to complete and interpret profile feature control frames to achieve various levels of control, including composite and non-uniform specifications. Additional topics include using profile to specify coplanarity, controlling conical surfaces, and applying dynamic profile tolerances. You also sketched tolerance zones, creating by different profile applications, and explain the role of datum feature references in establishing constraints. Okay, in conclusion, by the end of this lesson, you were able to define line and surface profile tolerances, apply profile tolerances to define allowable variation within a limit zone on a feature or across all of a feature, apply a profile tolerance to extend all around the profile of a part, apply a profile tolerance to extend all over a part or to all surfaces, complete profile tolerance feature control frames to achieve the allowable levels of control and combine them as needed. And you also learn to draw a composite profile tolerance specification. Okay, we specified coplanarity requirements using profile tolerance. We also applied a non-uniform profile tolerance, identified profile tolerance as a means for specifying allowable variation for conical surface form, orientation, and location, and apply a dynamic profile tolerance, and sketch the tolerance zones created by each of the possible profile tolerance specifications, and explain the constraints established by datum feature references. This concludes this lecture, which is the last one for this course. And thank you for sticking with me. This is a thick subject matter, and we'll catch you on the next topic in a future class. Thank you very much, and have a good evening.